Welcome to The Explainer. Today, we're jumping into the ultra-competitive world of high-frequency trading to see how programmers use C++ to shave off billions of a second. We're going to find out how they gain an edge where every single nanosecond can be the difference between making millions or losing them.
And believe me, that is no exaggeration, especially not in high-frequency trading, or HFT. This is a world where latency is everything, and the laws of physics are your real speed limit.
All right, let's kick things off with our first section, the HFT nanosecond race. We're about to see just why this is a game played in billionths of a second.
So what exactly is HFT, officially? Well, the U.S. Securities and Exchange Commission boils it down to a few key things: using super-fast computers right next to the stock exchange, holding on to stocks for just fractions of a second, and trying to end the day with zero risk. But really, it's all about two things: speed and volume. This table, wow, it really lays out the battlefield for us. Just look at the difference. Getting data from the CPU's fastest cache, that takes half a nanosecond. But getting that same data from main memory, 100 nanoseconds. That's 200 times slower. That gap is everything. It's where this race is won or lost.
Okay, so now that we know the stakes, let's get into the really cool stuff. How C++ programmers basically bend the hardware to their will to win this race. See, the secret isn't just about writing good code. It's about writing code that deeply understands the machine it's running on.
So in any system where speed is king, you have to separate what's called the cold path from the hot path. The hot path is the sequence of code that actually executes a trade. It's the moneymaker. It has to be as fast as humanly possible. Everything else can wait. And this focus leads us to a really clever technique called cache warming.
Okay, so check this out. On the left is the cold approach. The code just sits there waiting for a trade signal. When it finally comes, you might have to pull everything from that slow main memory. But now, look at the right, the warm approach. Here, the logic is constantly running, processing every bit of market data. It doesn't actually trade, but it makes sure all the important instructions stay loaded in that ultra-fast CPU cache, ready to pounce instantly.
And the result? It's absolutely staggering. The benchmarks show that just by warming up the cache, the code runs about 90% faster. It's one of those non-intuitive tricks that has a massive impact, all because it's designed to work with the hardware, not against it.
Now, here's another powerful technique. It's all about doing your homework ahead of time. In C++, you can use a keyword called const express. This lets you tell the compiler, hey, figure this out now, so we don't have to waste precious nanoseconds doing it later when the program is actually running.
And the difference it makes is just night and day. Look at this. Calculating a factorial at runtime takes almost 2.7 nanoseconds. By using const express, the calculation is already done, the result is baked in. The runtime cost, it plummets to under a quarter of a nanosecond. That's over 90% faster, all because the work was done ahead of time.
And these are just a couple of examples, right? The paper we're looking at benchmarked over a dozen of these techniques. You've got loop unrolling, giving a 72% speed up, lock-free programming with a 63% improvement. There's a whole toolbox of these tricks, and they all offer these incredible performance gains.
So these individual tricks are fascinating. But what happens when you start combining them? When you apply them to an actual real-world trading algorithm? Well, let's take a look.
The researchers implemented a classic strategy called pairs trading. The idea is pretty simple. Find two stocks that usually move together, kind of like dance partners. In this case, Goldman Sachs and Morgan Stanley. When one zigs and the other doesn't zag for a moment, you trade on that temporary split, betting they'll get back in sync soon.
And the results? They are just mind-blowing. The standard, non-optimized code took over 500,000 nanoseconds to execute. A lifetime in this world. But after applying those C++ tricks we just talked about, they slashed that latency all the way down to just over 65,000 nanoseconds. That is a staggering 87% reduction.
But it's not just about optimizing one algorithm, is it? Entire systems have to be built for speed from the ground up. And this needs to some incredibly advanced designs, like a pattern called the LMAX disruptor, which was born in the world of financial exchanges.
At its heart is something called a ring buffer. Just picture a pre-allocated circular conveyor belt. This allows different parts of a program to add and remove data at the same time without bumping into each other, which avoids a huge bottleneck that plagues a lot of systems.
And the benchmarks speak for themselves. To process 10,000 events, a standard queue took 9.7 million nanoseconds. The disruptor did the same job in 4.3 million.
That's more than twice as fast. It achieves this by cleverly avoiding system locks and making the absolute most of the CPU's caches.
So after looking at all of these incredibly clever techniques and design patterns, what's the big takeaway? What's the fundamental lesson here?
It all comes down to this. These techniques aren't just abstract C++ tricks. They are deliberate, careful ways of controlling how your code and data are laid out in memory. It's about designing your software to work with the hardware, not against it. That's how you squeeze out every last drop of performance.
It really makes you wonder, doesn't it? How much hidden speed is just sitting there, dormant, in the software we all use every single day, just waiting for someone to come along who has a deeper understanding of the machine it actually runs on.